All right, let's talk about Chapter 6, work. Ugh, work. Work is defined as the force that's on an object times the distance that it travels. This is work. So here's my little car. Let's apply a force on it over some distance. Let's take it to here. Now, there we go. I pushed it. My force of my finger started here, and I pushed it across that delta x. That means I had a force of some measured in newtons times the delta x, which is measured in meters, which is a newton meter, which I will call a joule, named after James Joule. There we go. Work is always described as being done on an object. Here's my car again. I did work on the car. Here it has initial velocity of 0. After I do work, it keeps moving. Something that work was done on the car. I did something to the car and did, what did I do? I did work. So let's take something else here. Let's take a box. Yeah, here's a little box. And I'm going to move it some delta x. But now I'm going to tie a rope to it here and kind of, but I'm going to pull it up at some angle. So I'm going to have a force in this direction. Now I only want the force that goes in the direction of the displacement. So then work becomes force times the displacement. Technically it's the dot product, but since we haven't done that too much, cosine f delta x cosine theta. So notice when theta equals 90, there we go, no work is done. So if this thing is sliding sideways and I'm lifting up on it, that force didn't do any work. So now let's go back to my car here for a second. This is a really heavy car, 3,000 kilogram car, and it's going to accelerate at 1.5 meters per second squared over 65 meters. So I'm going to start here and then go to 65 meters. All right. How much work is done on a car? Well, work is force times the displacement times the cosine of the angle between them. My angle is, so my force, it's going this direction. So my displacement is in this direction. The angle between them is 0, so that goes to 1. Now it's force times distance. Well, I don't really have the force, but I have the mass. So F equals ma. My acceleration and how far it goes, ma delta x. So my mass is 3,000 kilograms times the acceleration of 1.5 times the distance that I go, 65 meters. And misplaced my calculator. This turns into something. 6,000, half of that is 45,000 times 65, 0. Oh, let me knock this out real quick somewhere else. Maybe I could do a little dance. Oh, you can't see me. Times 65 equals 292,500 joules of work were done. But something had to happen. When this accelerates up, the car is now I'm accelerating, I'm changing my speed. Something is happening there. So this is what's called the work energy theorem. What does that mean? Well, when you do work, you're doing something. something changes. So, but what changes? Let's do a little algebra. So work is force F delta x. F is ma delta x. Man, where have I seen that a delta x somewhere? I know where. V final squared equals V initial squared plus 2a delta x. Let me do a little manipulation here. V final squared minus V initial squared equals 2a delta x. Let's divide both of these by 2. So now I have V final squared minus V initial squared over 2 equals a delta x. Let's substitute this into here. So now work is mass times, well, V final squared minus V initial squared all over 2. Let's multiply this out. So I'm going to have, I'll push the 1/2 out, 1/2 m V final squared minus 1/2 m V initial squared. Hey, wait, a final minus initial, something changes. That's a change in this kind of 1/2 mv squared thing. It's moving. It has mass. Moving, I like that. Let's use some Greek. Now I got its kinetic something. Let's call it energy. Let's just make up a word. Kinetic energy. Work causes changes in kinetic energy.